So far, we have discussed rotational kinematics and moment of inertia, the resistance of an object to changes in spin rate. We are now ready to explore forces that cause rotation, which are known as torques. Let's see an everyday example. When you open a door, you're applying a force to make it rotate around its hinges. But you apply this force in a very specific way. You always push the door at the handle side, never at the hinge side. The placement of the force matters when you are rotating an object. The further the force is located from the hinge point, the easier the door is to rotate. Or, to be more precise, the further the force is located from the hinge point, the easier it is to produce an angular acceleration. The closer the force is exerted to the hinge point, the harder it is to produce an angular acceleration. And if you push the door such that your force passes straight through the hinge point, you will not be able to spin it at all. Its angular acceleration will be 0. At this point, we've seen rotational versions of displacement, velocity, and acceleration. We've also seen moment of inertia, which is the rotational version of mass. Now we are ready to explore the rotational version of force. It is called torque, and it is symbolized by the Greek letter tav. We will visualize it using this image of a door and its hinges as seen from above. A torque is a force that doesn't pass through the center of rotation, whether the center of rotation is the center of mass or a hinge point. As we saw, torque has to account not only for the size of the force, but also for its distance and orientation relative to the center of rotation. To find torque, draw a vector from the center of rotation to the location where the force is applied. In this visualization, the force will be applied about 2/3 of the way down the door. This vector is symbolized by the letter R and is known as the lever arm. Multiply that by the size of the force. Then multiply that by the sine of the angle between them, not the cosine like what we did for work. Here it's the sine. That gives you the torque. My 103 students saw this operation a few videos ago. It is symbolized in shorthand like this. It is called the cross product of the lever arm and the force. Torque is measured in newtons times meters. This can be a bit confusing because previously, when we were exploring work and energy, the units there were also Newton meters, also known as joules. But joules only apply to scalars like work and energy. Torque is a vector. We use the same convention as we did in rotational kinematics. If we draw a picture and the force looks like it would rotate the object counterclockwise, we consider it a positive torque, and its direction is in positive k hat. If the force looks like it would rotate the object clockwise, it is a negative torque, and its direction is negative k hat. Equivalently for my 103 students, we would use the right-hand rule, which we introduced in cross products. If you use the right-hand rule, always make sure you align your hand with R and curl your fingers in the direction of F. Order matters when you're taking a cross product. If you get the order of the vectors wrong, you'll get the wrong direction when you do the right-hand rule. Let's apply our knowledge of torques to this example. A wrench is 0.3 meters long and oriented rightwards. It is used to rotate a nut. Calculate the torque if a 20 Newton force is applied A, 0.15 meters from the nut pointed upward, B, 0.3 meters from the nut pointed upward, C, 0.3 meters from the nut pointed at 135 degrees, D, 0.3 meters from the nut pointed leftward, and E, 0.3 meters from the nut pointed downward. In this question, we have a wrench, and it is going to tighten something like a hex nut. So let's say the wrench looks something like this. I consider that one of my better drawings, so I hope you appreciate that. We're going to put the origin at the center of rotation. That's what we usually do in a rotation question. The center of rotation is the hex nut. So that means that the y-axis looks something like this, and the x-axis looks something like this. And we were told that the force is going to get applied at two different points. For part A, the force gets applied midway down the hex nut, that's 0.15 meters. And for parts B through E, the force is being applied at 0.3 meters. Finally, there is the force itself. Now, in part A, it's going to get applied over here. In part B, it's going to be applied over here, like this. So I'm just going to start labeling these. This is A, this is B. For part C, the angle has changed. It's pointed at 135 degrees, something like this. For part D, it points in like this. And for part E, it points something like this. Now, the last thing we were told was that the size of the force in all of these cases is 20 newtons. So given all of this information, we are ready to calculate what all of the torques are. Let's start with part A. Now, here we have a force of 20 newtons at a position of 0.15 meters from the center of the hex nut, from the center of rotation. So, because torque is equal to the distance from the center of rotation to the point where the force is applied, that's known as the lever arm, multiplied by the size of the force, multiplied by the sine of the angle between them. We'll talk more about that sine in just a second. First, let's put in the information that we know. So the lever arm in this case is 0.15, that's the distance between the center of rotation and where the force is being applied. The force itself is 20 newtons, times the sine of the angle between them. The lever arm is stretching rightwards from the hex nut, and this this force of 20 newtons is pointing upwards. So, if we consider the lever arm as pointing rightwards and the force is pointing upwards, that means that the angle is 90 degrees between them. So we have the sine of 90 degrees. So the size of the force now becomes 0.15 times 20 times the sine of 90 degrees. The sine of 90 degrees happens to be 1, so this is just going to simplify down into 0.15 times 20 times 1, which is equal to 3. And this is measured in newtons times meters. So now we know the size of this torque. The last part of this is to figure out what is the direction of the torque. Is it a clockwise torque or is it a counterclockwise torque? So far we've only found the magnitude, the size of the torque. Well, the answer goes like this. If you're in my 101 class, let's visualize this force over here pushing on this wrench. A force like this would cause the wrench to spin in this direction. That is counterclockwise. So that would be a positive torque. And you would write the answer as 3 k hat newtons times
meters. Cool. If you're in my 103 class, we would analyze it in a slightly different way, but we would end up with the same result. And the way that we would analyze it is something like this. We would use the idea of the right-hand rule. The right-hand rule goes like this. Take your hand and align it with the lever arm. So that is starting from the nut and going to where the force is applied. That's the direction of the lever arm. Then curl your fingers in the direction of the force that's being applied. That's 20 degrees like this. And then extend your thumb. My thumb is right now pointed out of the page. And a vector that is pointed out of the page is considered to be in the positive z direction. The positive z direction corresponds to k hat. So that means that once again, we have confirmed using the right-hand rule that this is indeed the correct torque. Now, let us try it for the remaining ones over here. For part B, the size of the torque is going to be given by lever arm is now 0.3 because the force is being applied 0.3 meters away from the center of rotation, times the force is still 20 newtons, and the angle at which it is being applied is still 90 degrees. The orientation has not changed. So, when you simplify all of this, you get 0.3 times 20 is 6. And this is still going to be in newtons per meters. And this force, if you were to apply this force to this wrench like this, it is once again going to cause counterclockwise motion. And we can confirm this using the right-hand rule for my 103 class. Lever arm looks like this, force points like this, thumb points like this. So that's out of the page. That is, once again, the positive k hat direction. That is a positive counterclockwise rotation. And so we get that the torque in this case is 6 k hat newtons times meters. Let's keep going. What about C? For C, the torque is given by the distance from the center of rotation to the point where the force is applied is still the same. It's still this 0.3 meters. The force being applied is still the same 20 newtons, but this time the orientation has changed. The orientation was 90 degrees over here, but if we draw this vector here for the lever arm in the positive x direction, this is pointing at 135 degrees from that. So this is the direction of the lever arm, this is the direction of the force. So now we have sine of 135 degrees. So when you solve all of this out, you get 0.3 times 20 times the sine of 135 degrees. So 0.3 times 20 times the sine of 135 gives us 4.42 newtons times meters. Now, let's expand this somewhat. We still have to find what the direction is. This force, even though it's pointed at an angle, would still tend to rotate this wrench counterclockwise. It just won't do it as effectively as if you had been pushing at 90 degrees. So that means because this is moving counterclockwise, that means that this is still a positive torque. And we can confirm this with the right-hand rule. The lever arm points rightwards, and the push from this force over here, the push from this force is pointed in this direction. your thumb still points out of the page, so that it is indeed a positive counterclockwise torque. Let's move on to D. For D, the size of the torque is given as the lever arm, still 0.3, times the size of the force, still 20, times the orientation. So this time, the lever arm is pointed rightwards, the force is pointed leftwards. That's exactly 180 degrees. So that works out to 0.3 times 20 times the sine of 180, but the sine of 180 is 0. So you end up with no torque at all. And that should make total sense, because this force is now pointed in line with the lever arm. This force is now passing through the center of rotation. And like we saw with the door example from earlier, when a force passes through the center of rotation, it isn't capable of producing rotation. It might be capable of moving the wrench, it might be capable of displacing the wrench, like shearing it off whatever nut it is attached to, but it is not capable of rotating the wrench. So we end up with a torque of 0. Finally, part E. Here, the size of the torque is going to be given by the location of the force is still 0.3 with respect to the center of rotation. The size of the force is still 20. This time we would say the angle between them is lever arm points like this, the size of the force, or the force itself, points downwards like this. That's a 90-degree angle. So that is going to work out to 0.3 times 20 times sine of 90 degrees, which is what we worked out over here. So that's still 6 newtons times meters. Now to find the direction. A force like this is pointing in the opposite direction to something like B. If we were to follow this force, it's going to cause this object to move something like this. That is the clockwise direction. That's the negative direction. So correctly, we should call this negative 6 k hat. And for my 103 students, we'll analyze it using the right-hand rule. The lever arm points like this, but the force points downwards like this. Now extend your thumb. Kind of like this. Maybe you can see it if I angle it a little bit. My thumb is now pointed into the page. And if that's the case, that corresponds to a negative counterclockwise torque. So we have now solved for the size of the torque in each one of these different cases. And we can see some patterns over here. As the distance of the force away from the center of rotation increases, the torque also increases. But as the angle gets further and further away from 90 degrees, as it goes from 135 to 180 and so forth, you end up with a smaller and smaller torque until the angle of the force is exactly opposite the angle of the lever arm, and then you end up with 0 force. And finally, we have seen a case where you end up with a negative torque because it's oriented in such a way that it produces clockwise rotation.
In this video, we were introduced to the idea of torque. In the next video, we will use it in concert with Newton's laws.